Hey everyone, welcome! Today we're going to do something really useful. We're going to break down a full electrolysis question from a past GCSE chemistry paper, and we're going to use the official mark scheme to show you exactly how to get every single mark.
So here's the game plan. We'll walk through the whole thing step by step. We're going to cover everything from some basic definitions and half equations right through to analyzing experimental data and smashing that final calculation. All right, let's get into it.
All right, first up, we're starting with a pretty fundamental 2-mark question that's really just testing your core understanding of the difference between electrolysis and a chemical cell.
Okay, so the first thing to clock is that command word explain. Now that's a signal, right? It means you can't just list stuff. You've got to show you understand the contrast between these two things, really focusing on the role of electricity and chemical reactions in each one. And boom, here's the perfect 2-mark answer, straight from the horse's mouth. The mark scheme. You get 1 mark for each clear statement. Really, the crucial point is that they're just opposites. With electrolysis, you put electricity in to force a chemical reaction to happen. With a cell, you use a chemical reaction that happens naturally to get electricity out.
Now, what's really cool is that the mark scheme isn't super rigid. It shows that examiners will accept other words too. So if you wrote voltage or current instead of electricity, you're totally fine. You still get the mark. This is why knowing how these mark schemes work is like a superpower for exams.
Okay, so that's the basics down. Let's build on that now with something that comes up all the time. A classic half-equation question.
So you're given the bromide ion, Br-. The goal? Show how it turns into a bromine molecule. And, first thing to remember, bromine hangs out in pairs, right? It's Br2. And the really important part is making sure everything balances, both the atoms and the charges. And here's what the completed equation looks like. You get 1 mark for just knowing the products are Br2 and electrons, or E-. But that second mark, that's for the balancing. Since you need 2 bromine atoms to make 1 Br2 molecule, you have to start with 2 bromide ions. And those 2 negative charges become 2 electrons on the other side. Perfect!
All right, moving on. This next bit really tests if you know your rules for electrolysis, especially in aqueous solutions. Because remember, the moment you add water, you've got H+ and OH- ions in the mix, and they can change what gets produced.
So the task is simple. Fill in 3 gaps in this table. You've got to predict the products at both electrodes for 2 different salt solutions. Let's see what the mark scheme is looking for. And here we go. This is the filled-in table. So, for copper nitrate, getting oxygen at the positive electrode, that's 1 mark. Then, for potassium iodide, you need iodine at the positive and hydrogen at the negative. That's another 2 marks, 1 for each. A nice quick 3 marks if you know your rules.
Okay, now we're getting into the bigger stuff. A longer question based on an actual experiment. This is where you have to take your theory and apply it to what's happening in the lab.
So first things first, let's just get our bearings with the setup. We've got our power supply, an ammeter to keep an eye on the current, and then our 2 inert electrodes just sitting in a beaker of copper nitrate solution. Pretty standard stuff.
Now, this is a really good question because it's all about practical thinking. In the real world, experiments don't always go perfectly. Here, things have gone a tiny bit wrong. Some of the copper fell off. So how do you make sure you find the total mass of copper you made, not just the stuff that stuck?
And the mark scheme gives you this beautiful, clear 4-step method, a mark for each step. First, you've got to filter the whole mixture to separate that solid copper at the bottom. Then, of course, you can't weigh wet stuff, so you have to wash and dry it. Step 3, weigh what you've collected. And for the final step, you just add that number to whatever mass the electrode gained. Simple.
All right, next up, we've got to put on our data analyst hats and look at this graph. So on the y-axis, you've got the total mass of copper produced. Along the x-axis is time. And those 3 lines, each one represents the experiment run at a different current. So the question is about direct proportionality with time. What does that actually look like on a graph? What's the one key feature you need to spot to prove something is directly proportional?
And there it is. That's the key. For that 1 mark, all you need to say is that for any of the currents, the graph is a straight line and it passes through the origin, the 0, 0 point. That's literally the definition of direct proportionality in graph form.
Okay, same idea, but this time we're looking at the relationship with the current. Now look closely. The question specifically says use data from figure 5. That's a huge clue. If you don't pull some numbers from the graph to back up your point, you get 0 marks. Simple as that.
So here's how you nail that mark. First, you state the pattern. When the current doubles, the mass produced also doubles. Then you prove it with numbers. Let's see, let's pick a time. 20 minutes looks easy enough. Okay, at 20 minutes, find the 0.3 amp line. Yep, that reads across to 0.12 grams. Now let's look at double the current, 0.6 amps. At 20 minutes, that reads across to 0.24 grams. The mass doubled too. Perfect proof.
I like this next question. It's about connecting something you can actually see, the solution changing color, with the chemistry that's happening. So what actually makes copper solutions blue in the first place?
So here are all the ways the mark scheme says you could phrase it. The main idea, the absolute key, is that the blue color comes from copper ions floating around in the water. But during electrolysis, those Cu2+ ions get turned into solid copper atoms on the electrode, so they're being taken out of the solution. As their concentration goes down, the blue color just fades away. Any of those points gets the mark.
All right, deep breath, we're at the final boss, the big 3-mark calculation. Now these can look a bit scary, but trust me, if we just take it step by step, it's totally doable.
So here's our 3-step plan. Step 1, get the mass from the graph. Step 2, turn that mass into moles. And step 3, turn the moles into the actual number of atoms. Let's do it.
Okay, step 1. Back to the graph. We need the point for 20 minutes and 0.6 amps. So we find 20 minutes on the bottom axis, go up to that middle line, and read across to the y-axis. Yep, that gives us a mass of 0.24 grams. First part done.
Step 2, moles. The formula you need is moles equals mass over AR. We have our mass, 0.24, and the relative atomic mass of copper is given in the question. It's 63.5. So you just pop those numbers in the calculator, and you get 0.00378 moles. That's mark number 2 in the bag. And for the final piece of the puzzle, we need to find the number of atoms. The formula for that is moles times Avogadro's constant. We've got our moles from the last step, and the Avogadro constant is always given to you. So we just multiply them together. And that gives us our final answer, 2.28 times 10 to the 21 atoms. And, hold on, the question asks for 3 significant figures. Is our answer in 3 sig figs? Yes, it is. Phew! Don't forget that final check. It's such an easy mark to lose. And that is how you dismantle a full electrolysis question, mark by mark. So what's the big takeaway here? It's that the marks are always in the details. Are you spotting the command words? Are you using data when they ask you to? Are you checking for things like significant figures? Get those details right and you'll absolutely smash it.